Hello, welcome to what this is going to be the lesson on the Leslie model and population growth. So we're about at the end of our matrix unit. We have really two more application problems where we're just going to be using matrices to solve problems. And the first one is this problem of population, where population of bighorn sheep in the Rocky Mountain National Park is currently under protection by the Colorado Fish and Wildlife Department. However, more recently, biologists have been concerned about whether the sheep will continue to grow in numbers in future years. They know that this is highly dependent on the birth rates and survival rates of the sheep at different stages in their life. And this information is below. So, for these problems, you're going to be given a table or a chart of this age groups. So you see there in every 2 years, birth rates and survival rates. And with this, we can create, and I'm going to be calling it a Leslie matrix, and you'll see that in a minute, because the guy who created this whole thing was last name Leslie. But we can track their population over years in front of us based on this information and based on knowing what the population is now. And we'll see that next. But just so you understand what the chart is giving you, these deer, or these sheep, I'm sorry, there's deer later. These bighorn sheep go anywhere from 0 to 12 years old. And you'll see that after 10 to 12 years, none of them are surviving. So that's the lifespan of the deer, no more than 12 years, right? The babies, the 0 to 2-year-olds, they don't have any babies, and about 60%, well, 60% of them are going to live. 2 to 4-year-olds, and what this fails to mention, and what some of them do, this is always going to be female population. It's based on the female population. So, but for the 4-year-olds, they are going to have, I guess you could look at this as 80% of them are going to have one baby, or they're going to count for 80% of their group having birth, right? And then 80% of them are going to survive. When they get up to 46-year-olds, then they're going to have, each one of them is going to have 1.2 babies. So in that 2-year period, they're going to be giving birth to more than one on average. Not a whole lot more, but. And 90% of them survive. And then from the 6 to 8-year-olds, they're going to be given almost two babies every 2 years. And 90% of them are going to survive. And then 8 to 10-year-olds, that birth rate drops off, survival rate only 70%. And then, like we said, none of them are going to survive beyond 12 years. So let's look at how that works with the population we know. So right now, the current population of sheep is 130. If you added these up, that'd be 130 sheep. And there's that same chart, right? So if you think about like this population moving forward, I'm going to spread it out a bit. The 0 to 2-year-olds, change that to color, 2 to 4s, 4 to 6, 6 to 8, 8 to 10, 10 to 12. So right now, which would be in year 0, we have 50, 30, 18, 18, 10, 4. So the next cycle would be for this group to move up, it's going to be 2 years later. So in 2 years, we're going to look at the population again. And the reason we're doing, because they're in 2-year groups. So we know in 2 years that all of these 0 to 2-year-olds are going to be up here in the 2 to 4-year-olds, right? all of that group will be, so it's going to take absolutely for sure 2 years will move everybody up. Well, in 2 years, the deer that are, or the sheep that are in the 0 to 2, those are the new babies. So those are based on the birth rates. So you'd have to look at like those, if you think about birth rates, those 50, right? They're having no babies. So we don't even have to worry about the babies having babies, right? These 30, they're going to have 80% of them are going to have a baby. So 80% of 30, when you multiply that, is 24. These 18 and the 4 to 6 year olds, they're going to have 1.2. So 18 times 1.2, it's 21.6. I'm not going to round it right now, but when we're done with all of this, we are going to round to the nearest whole sheep to keep everything. So the 18 6 to 8 year olds, they're going to have 1.7. So 18 times 1.7, they're going to have 30.6. Those 10 that are in the 8 to 10 year olds are going to have 0.8. That would be 8 babies. And then the 4 are going to have 0.4, which is 1.6. So the total number of babies, this is just all babies, all right, 0 to 2 year olds, would be 0 plus 24 plus 21.6 plus 30.6 plus 8 plus 1.6. Again, 1, 2, 3, 4, 5, all 6 age groups. So that's, this adds up to, when you add up all of this, 81, 85, 85.8. So we're going to round that and say, okay, now there's going to be 86. After 2 years, there should be 86 children. And whether they were born right at the beginning of the cycle or late, they're still going to be in that 0 to 2 year old group in 2 years. So where are the 2 to 4 year olds coming from? Well, that's this group aging up to the next group. And not all 50 of them will make it there. That's where we use their survival rate. If you think about those 50, if 60% survive, 50 times 0.6 is 30. So of those 50, only 30 will survive. These 2 to 4 year olds are going to be the ones that move up to the 4 to 6 year olds. So those 30, that would be 30 times, if you're a 2 to 4 year old, your survival rate is 0.8. So 30 times 0.8, 24. So 24 of them will survive. Well, these 18 4 to 6 year olds, 90% of them are going to survive. So 18 times 0.9 is 16.2. 16. These 6 to 8 year olds, 18 of them have a 90% survival rate also, right? So that also is 16.2. 16 of them are, and then the 10 of these have a 70%, so 10 times 0.7 is 7. So 7 of them will move up to that age group. And then, of course, those 4 aren't going to survive, so we don't have to multiply times 0. So this would be your new, what's called population distribution after a 2-year period. So now if I wanted to do a 4-year period, I'd have to repeat all of that again. But since it's the same multiplication, right, we can put this into what's called matrix form. And we can get this information just as easy. Let me show you how that works. Page down here a little bit. All right, so there we go. We're going to take that initial population information that I started with, and it is going to be called your, it's piece of O. That O is really 0. That is the population at the beginning. And it's going to be a 1/6 matrix to show all those populations. And they were, start out with 50, 30, 18, 18, 10, 4. So 50, 30, 18, 18, 10, 4. Initial population of each age group. Then I need what's called a Leslie matrix. And this matrix, we could call it an L matrix. We'll probably put them in the calculators just A and B, but it's going to be a 6/6. This Leslie matrix, 6/6. So in matrices, if we're going to multiply, you are going to have row times column, row times column. So, and then that first row times column is going to drop out a new, if we're doing a 1/6 times a 6/6, then the matrix we're going to end up with is going to be a 1/6, and it's going to be to the new population distribution. So the first row times the first column is going to give you that first spot again, which is the babies. And how did we get the babies? Well, we did 50 times 0, 30 times 0.8, 18 times 1.2, 18 times 1.7, 10 times 0.8, and 4 times 0.4. So that first column, then we added them all together. Well, that's what matrix multiplication does. It'll multiply each pair and then add them all up, and that'll be your first number. So these are your birth rates going straight down that first column. Well, to get the second number, right, in your 1/6, to get this number back, well, that's the 50. That's the first group moving up into that age group based on their survival rate. So if I want to multiply the 50 times 0.6, then I have to put that survival rate number first on top, right? Because it's the number that were 0 to 2, how many survive, this will move them into the second column. Well, I don't want to include how many survive from the 30 from the second group or the third group or the fourth or fifth, right? So all I want is the 50 times 0.6. So the rest of these, I'm not going to include in that. So they won't add up. It's just the ones that survive. Well, for the 30, how many of them survive? Okay, so for this next group, like I said, the 30 in the second group, 80% of them will survive, and they're going to be in this third column. So this third column is going to be the 80% that survive. So to get the 30 to multiply by 0.8, I need that 0.8 in the second row, and then not worried about anybody else. And so you can see the pattern. The 18 have to multiply the first 18. Well, actually, both of them are 0.9, so, and that would be the third number. 90% of them survive. And then the fourth group, 90% of them survive. And the fifth group, we had 70% of them survive. Now, the last group I'm not going to put on here, one, because I've used my 6, right? I've already got a 6 by 6. I don't want to go to a 6 by 7 because then um, you'll see later, but that group is going to die off anyhow. We don't want an extra group. And it's important to keep this as a square matrix, a 6 by 6. So that would do it. So let me show you on Desmos how exactly that looks. So on Desmos, you are going to do your matrix calculator. So your okay, so we are going to have a new matrix here. And that first matrix, I want to do the um, initial population matrix, which was a 1 by 6. And 6 is as most as we can go, so it was 50, 30, 18, 18, 10, 4. So there's our initial one. I put that in the A matrix. You could put it in any matrix. Just remember which is the initial one. And remember, when you hit clear all now, it will clear those. So you don't want to clear all until you're done with the entire problem. So I'm going to put the Leslie in this B matrix. And I need a 6 by 6. So this first row going down is going to be your birth rates. So that's 0, 0.8, and you have to click on it if you want to go straight down. 1.2, 1.7, 0.8, and you can put the 0 in there, 0.4, doesn't matter. And then the survival rates, they go diagonally. So the first survival rate is 0.6, and then it's the next in this diagonal. So down and over, 0.8. The next survival rate is 0.9, and then 0.9, and the last one is 0.7. Now, a lot of people get bothered that this does not end in the corner there, and it won't. That'll always be a 0 at the in there, and that diagonal will end one above it. And again, we can't do it in here, but if you're using another type of matrix calculator, don't put a 7th column in there because it's not going to work for what we're going to do here in a minute. So when I do A times B, there's those numbers we got. The 85, I rounded out to 86, right? 30 of them, 24, 16.2, we made 16 and 7. So that would be the population in 2 years' time. So if I wanted the population in 4 years' time, I would take this 2 years and do it again. How many of these are having babies? And then how many are surviving and moving up? So I would have to take the A times B, right? Which is that, and multiply it times that B matrix again. So now in 4 years' time, we're going to have 96, 51, so forth population. So if I multiply again, that would be 6 years. 2, 4, 6, 8 years, there's your populations, and so forth. So again, it's going to be 2, 4, 6, 8, 10. And then that, right, since we're just multiplying the B over and over again, we don't have to keep listing those out. If I want 10 years, 2, 4, 6, 8, 10 years, I can do A times B to the, there it is. What power would I use for 10 years? Well, fifth power. And that's important to understand. You're going to get the same thing, and then you can just round off each one of those numbers for the population. But that's important to remember that that power, when I come back here, and we're going to look at the next page. So that power is how many what are called cycles. And for this first population situation, every cycle represents 2 years because all of their births. And so each time we have this type of problem, their age groups are all going to be the same. So we have our Leslie, we have our initial population, and we need to remember that pencil working, one cycle equals 2 years. So what will be the population distribution in 10 years? Well, 10 years, I would divide by 2. That's going to be 5 cycles. So to get that 10 years, I'm going to do my initial population times that Leslie matrix to the 5th power, which is what I just did on Desmos. I'll write those down so I can transfer them over. Right, so that would be 198, 91, 59, 42, 33, and 14. So that was 198, 91, 59, 42, 33, 14. That's the distribution. So if I ask you for a population distribution, that's what it's saying. How many are in each age group? Okay. When I get to part B, what will be the population of the 6 to 8-year-olds in 16 years? Well, 16 years, I'm going to have to divide by 2. So this will be 8 cycles will make 16 years. And then for the 6 to 8-year-olds, remember that 0 to 2, 2 to 4, 4 to 6, 6 to 8. It's that fourth number. So I don't 1, 2, 3. I want to know what's the fourth one for the 6 to 8-year-olds. Right? 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. So just that number. So I'm still just going to go back. And now A times B to the 16 years is 8 power. And I just want the fourth number, looks like 86. So there would be 86 sheep in that group, right? So if it just asks for a specific age group, but in C, what's the total population? Well, the total population is going to be all of them. So in 20 years, it's going to be our initial population. 20 years will be to the 10th power, 10 cycles. But now I want to add all of them up. And we can do it by hand, or we can make it easy by doing a third matrix. So if you ever want to total a row matrix, then create a column matrix, and this would be a 6 by 1, of all ones, 6 ones. This way, when you get this information and you multiply it times that last C, when you multiply, you're not changing the number, but then it will total them all up. So what is the total? So this you're going to do times that C matrix, or what you might see as, I might call that a T matrix for total, but I'm going to put it in the calculator as C. So when I go back over to the calculator, I want a new matrix. I want it to be a 6 by 1 with 1, 1, 1, 1, 1, 1. So now for 20 years, I would do my initial times my Leslie matrix to the 10th power, right? Make sure you get out of that exponent times, so let's go back. This is all of the population. Like I said, you could add those by hand. Don't round them, go a couple decimals because you're going to get a rounding error, or use that third matrix and it will total them for you. So it looks like I have 1,400 sheep. So what will the total population be? 1,400 when you round that. After, don't round until the end of the problem. All right, and then look at D. So how many years will it take the population to reach 4,000 sheep? So for this one, you don't know what the exponent is, but you want the total population to be greater than, to exceed 4,000. So this is a guess and check problem. You're just going to have to go over to your matrix calculator and say, well, I know that at 10 that we're only to 1,300, 1,400, right? So let's say you did to the 20. Just try 20th power times C. So that is 14,000. So I've gone well over. So now I can just go back and manipulate this exponent. I don't have to keep changing. So if 20 was way too big, let's say 15. So 15, and it was over 4,000, right? So 15 put them over 4,000, but make sure, let's check 14. Yeah, so 14 does not. So 14 is too low, so 15 is the first number of cycles that puts it over 4,000. And if that, if 15 was too low, you keep checking, but it's easy to guess and check by just changing that exponent when you're multiplying by C. So the question is how many years, not how many cycles. So we figured out that it's going to take 15 cycles to make that happen. So how many years is that? Well, if one cycle is 2 years, then that will be 30. All right, kind of got cut off there. So, like I was saying, um, we figured out that the number of cycles was 15 to get to 4,000 sheep. So the number of years that they're asking for would be 30. You'd have to double your cycles. 30 years. All right. So it's you're just going to go to, I'll show you another problem, another example. So this is number 2 on your assignment. Now you have a small herd of animals, and they're from 0 to 3, 3 to 6, 6 to 9. So one cycle here equals 3 years. So we're not multiplying ourselves. When we have these population, go straight to your matrices. So your initial population will be given. You need it. That's 20, 22, 30, 40, 28, 16. Your Leslie matrix, which again, if there are 6 population groups, then it's going to be a 6 by 6. Your birth rates go straight down the first column. So birth rates are 0, 0.4, 0.7, 0.9, 0.8. Am I doing that right? Wait. Look at, yeah, 0.2. 4, 7, 9, 8.2. Then your survival rates start at the top of the next column and go diagonally. So that'd be 0.7, 5, then 0, 0.9, 2, 3, 4, 0, 0, 0.9, zeros, 0, 0, 0, 0.8, and then remember that's 5, so your sixths 0.50. And again, that survival diagonal is going to stop not in the corner. So, and then of course we want to do a total matrix for any questions that ask us about the total population with 6 ones. So let's go ahead and put those into, all right, so not using these anymore, so I'm going to go ahead and clear all and do a new matrix. So the first one was a 1 by 6 for my populations, and they were 20, 22, 30, 40, 28, 16. And then a 6 by 6 for the Leslie matrix. Remember, birth rate's going down, 0, 0.4, 0.7, 0.9, 0.8, 0.2. And then diagonally for your survival rates, 0.7, down and over 1, 0.9, 90% survival rate, 90.9, 80% survival rate, then 50% survival rate. I'll end in that corner. Then I'm going to go ahead and do a 6 by 1, 1, 1, 1, 1, all ones. All right, so now I can answer any of the questions. So if we go back, for number 2, the questions are, Find the population distribution in 36 years. So remember, one cycle, one cycle equals 3 years. Right? So if I have 36 years divided by 3, that is 12 cycles would make 36 years, right? So you want to do your initial population times your Leslie to the 12th power. It's a distribution, so you don't want to multiply it by your C matrix because you want all 6 age groups for a distribution. So A times B to the, what do we say, 12 power for 36 years. Write those down. So we have 271, 166, 134, or 132, 103, 70, and 30. So there we'd have 271, 271, 166, 132, 103, 70, 30. Find the total population in 45 years. Well, 45, 3 years is a cycle, so that's 15. So, and that's total population, so that would be your initial distribution to the 15th power times that T matrix to get your total. So that would be A times your Leslie to the 15th. Make sure you get out of the exponent times C. So it looks like 1171. So your total population is going to be 1171. Just round off. How many 6 to 9-year-olds will there be in 24 years? Well, 24 divided by 3 is 8, so that's 8 cycles. And 6 to 9-year-olds, remember the first group 0 to 3, 3 to 6, 6 to 9. So it's that third number over will be the 6 to 9-year-olds in 24 years. If you wanted to be kind of lazy, you know that this is A times B to the, I could do just whatever if I know, oh, not divided by 8, sorry, divided by 3, right? Because there's 3 years for every cycle. So that's the same as putting 8, if you want to look at it that way. Remember 0 to 3, 3 to 6, 6 to 9, there are 79 of those. So that would be your initial population to the 8th power and looking for that one number, which I already forgot it, 79. So 79. All right, how many years will it take the herd to exceed 2,000? Remember, that's that guess and check. So I'm going to do A times B to the 15 cycles. Didn't make it, so let's do 20 just to go up to the next times C. Oh, not 3 times C. So that exceeded 2,000. So what about, that's 19. And 19 does. What about 18? 18 does not. So it will be 19 will be so don't, if you guess something and it's over 2000, make sure you guess something smaller to make sure that very first time it goes over 2000, 19 cycles. So back here, that would be 19 cycles, but they're asking how many years. So every year, every cycle is 3 years, and 19 times 3 is 57 years. All right. So it took a lot of explanation, a lot of time to explain the first one, but as you can see, it really doesn't take long to do these problems. Once you know, start straight away, just put them into their matrix and then use those matrices. So I want to show you one more, only because the cycles are a little bit different. So be careful. In your third problem on your assignment, your cycles now are in months. So one cycle equals 6 months or half of a year. And so you have to be careful based on the way the questions are asked. Now you'd still say your initial population matrix will be all your populations, right? 100, 120, 210, 180, 150, 100. Your Leslie 6 by 6 going to be your birth rates. Make sure you, doesn't matter what order they put these in, that you do birth rates down the first column. So 0, 0.4, 0.9, 1.2, 1.0, 0.6, and then your survival rates start and go diagonally, right? So 0.7, it doesn't matter if they give you 2, 3 decimals, 0.8, 0, 0, 0, 0, 0, 0.88, just use, don't round, 1, 2, 3, 0.92, 1, 2, 3, 4, 0.76, and I've 1, 2, 3, 4, 5, I've reached my 6, I've finished where that diagonal always finishes, right above that 0. And of course, it's still a 6 by 6, so I still want 6 ones or whatever, right, for that total matrix. So over to Desmos, I'm going to clear all, get rid of those. New matrix is a 1 by 6. We said that is 100, 120, 210, 180, 150, 100. Then I need Leslie. So the birth rate's going down 0, 0.4, 0.9, 1.2, 0.6. Then your survival rate starting at the next one at the top, 0.7, and go diagonally. 0.8, 0.88, 0.92, 0.76. Then go ahead and do a 6 by 1, 1, 1, 1, 1. All right, so now answer the questions. And keep it in mind that one cycle is only 6 months. All right, so I said one cycle is 6 months, or one cycle equals half a year. So if you're asked for the population in 6 years, how many cycles would that take? So I know it's going to be your times a Leslie. What power would it be for 6 years? Well, if one cycle is half a year, then it's going to take 12. You have to double the cycles for years, right? And it's a distribution, so it's going to be all 6 different. All right, so we got all of our matrices in. So we're going to do the A times B to the, like I said, 6 years would take 12 cycles. And then the distribution. So it'd be 34, 38, 2002, 1329, 960, 720, 467. So definitely didn't give myself enough room for these big numbers. 3, 4, 3, 8, 2002, 1329, 960, 720, and 467. All right, so find the population distribution. So again, this is a distribution in 72 months. Well, there, it's in months. So if every cycle is 6 months, then you do 72 divided by 6. 72 is 12. So 72 months is 6 years. They're the same number. So they're going to end up being the same number of cycles. And it would be the same 3, 4, 3, 8. It's the same amount of time. So if it asks for months, you're going to need to divide by 6 for the cycles. But if it asks for years, you would multiply by 2. 960, 720, 467. Same question. Find the total population in 10 years. Years we got to double, so that'd be to the 20th. Total population times your total matrix. So you would do A times Leslie matrix to the 20th power times your C matrix. So it's going to be 40,298. 40,298. How many 24 to 30 months old will there be in 90 months? So 90 months, you're going to have to divide by 6 for the months. 90 divided by 6, that's going to be the 15th. Oh, 15th power. And then 24 to 30 months, so that's 0 to 6, 6 to 12, 12 to 18, 18 to 24, 24 to 30. So 24 to 30 is that fifth number. So if I want, so I'm going to have to look at initial 90 months is 15 cycles. Don't total it, but just look for that fifth number. So A times Leslie to the 15th and 1297. So 1297 is the one number we're looking for. And then finally, how long does it take? So remember, we don't know, but we are totaling it, and it has to be greater than 250. And the question is, how many years? Right? So first, let's figure out how many cycles. A times B to the 20th took us to times C. Okay, that puts us over. We're trying to get over 250,000. So I'm going to try 40. Let's see. Oh, that times 6 right here times 10 to the 6, that means a million. So this is 1.7 million. And I don't want 1 point, that's way too big. So let's try 30 cycles. Well, 30 puts me at 265,000. So that's still over. So let's go 25. 25 is not enough. 26 is 124, 27, 28, 182, 29, 219, 30 was the right number. So it's well over, but still 30 is the first amount of cycles. So how long it's going to take? 30 cycles. And each cycle is half of a year, so that would be, you could either look at it as multiplying by 6 for a number of months, or you divide that and say that's 15 years. So how many years? 15 years. All right, so the rest are up to you. Do your best, use that Leslie matrix, and it should be pretty simple to answer those questions. Just getting the cycles right is the big part of these questions. So good luck, and we'll go over it next time I see you.